Welcome to the second lecture on sequence and series. From the first lecture, it should be clear that by a sequence n is equal to 1 to infinity, written in expanded form as a1, a2, a3, so on, an, so on, we actually mean a function f from n to r. We are talking about real sequence, and various ways to describe a sequence, including the recursive formula where a particular term of a sequence is expressed in terms of one or more of its previous term. Now, let us try to represent a sequence using graph. Commonly, a sequence is represented by graphs in two ways. Consider the sequence n is equal to 1 to infinity. One way to represent this using a graph is to mark a few terms of this sequence on a real line. Let us say a1, a2, a3, and so on. A specific example will make it more clear. Consider the sequence n is equal to 1 to infinity, where an is given by root n. Nth term is given by root n. To represent this using graph, we plot the real axis. Here is 0, here is 1, 2, 3, 4, 5, and so on. The first term of this given sequence, namely an, with an as root n, is 1. So, this is a1. a2 is going to be root 2. It's less than 2, greater than 1. So, somewhere here. a3 is going to be root 3, which is greater than root 2. So, it is somewhere here. And a4 is root 4, which is 2. a5 is root 5, greater than 2 but less than 3. This is the graph of the given sequence root n. Let us see another example. Consider sequence Bn, n is equal to 1 to infinity, where the nth term Bn is given by 1 by n. To graph this, let us have the real line. See that B1 will be 1 by 1. B2 is 1 by 2. So, this is B1. B2 is 1 by 2, which is halfway between 0 and 1. B3 is 1 by 3, which is less than 1 by 2. So, somewhere here. B4 is 1 by 4, which is halfway between 0 and half. So, this is B4 and so on. You can see that the terms of this sequence coming nearer and nearer to 0. This is one way to represent a sequence by graph. Another way is as follows. Recall that a sequence is a function, and hence we can graph the corresponding function. To explain it with specific example, consider the sequence an, n is equal to 1 to infinity, where an is given by root n. We are going to consider the corresponding function f from n to r given by f of n is equal to root n, and we are going to consider the graph of this function. So, for that we consider the axis with n plotted along the x axis and an plotted along the y axis. Corresponding to 1, the value of the function is root 1, which is 1. So, the point is 1 1. Corresponding to 2, so let me mark the points on y axis which designates an. Corresponding to 2, the value of the function is root 2. So, we plot 2 comma root 2, 2 is here, root 2 is in between 1 and 2. So, this is 2 comma root 2, and corresponding to 3, the value of the function is root 3, which is less than 2 but greater than root 2. So, somewhere here 3 root 3. Corresponding to 4, the value of the function is root 4, which is 2. So, we plot 4 2 and so on, and these isolated points provides the graph of the function corresponding to the sequence an is equal to root n. This is another way to graph a sequence. Having said this, let us practice with some examples to grasp the basic concept of sequence. I am going to give some problems. Write first 5 terms of the sequence given by the formula an, the nth term of the sequence, is equal to n into n plus 2. I should admit that it's a bit confusing to say first 5 terms of the sequence, because we have remarked that a sequence can be treated as a function from n to r. In that case, the corresponding list will be a1, a2, a3 and so on, or it may be treated as a function from a subset of n to r. In that case, it is not necessary that the sequence starts with a1, it may be, for instance, a6, a7, a8 and so on. But unless otherwise specified, let us assume that the sequence start with n is equal to 1. That is, the list consists of A1, A2 and so on. With that agreement, we will find first 5 terms of the given sequence. A1, the first term, is 1 into 1 plus 2 obtained by just plugging n is equal to 1 is 3. A2 is obtained by plugging n is equal to 2. It is 2 into 2 plus 2, which is 2 into 4, which is 8. A3 is obtained by substituting n is equal to 3. So, 3 multiplied with 3 plus 2, which amounts to 3 multiplied with 5, which is 15. A4 is given by 4 multiplied with the number corresponding to 4 plus 2, which is 4 into 6, which is 24, and A5 is obtained by plugging n equal to 5 in the formula, 5 into 5 plus 2, which is 5 into 7, which amounts to 35. The list consists of 3, 8, 15, 24 and 35. These are the first 5 terms. If you want to write it as a sequence, it will be 3, 8, 15, 24, 35, etc., etc., and the number occurring in nth place will be n into n plus 2, etc. And it is always suggested to write, if possible, the term in the nth place as a function of n instead of just listing first few terms. What I mean is, for a sequence an corresponding to this problem, it is always suggested to list it as 3, 8, 15, 24, 35, etc., and then the nth place element n into n plus 2, etc., instead of just writing 3, 8, 15, 24, 35, etc. The reason, from the first few terms, the pattern may not be always recognizable. Let us proceed with the example. Find first 4 terms of the sequence given by the formula an is equal to n into n square plus 5 by 4. Of course, this is just numerical, but let us do it step by step, all the details. First term corresponding to this sequence, namely A1, is 1 into 1 square plus 5 by 4, which on calculation reduces to 1 into 6 by 4, which can be simplified into 3 by 2. Second term A2 is equal to 2 into 2 square plus 5 by 4, which on calculation reduces to 2 into 4 plus 5 by 4, which reduces to 2 into 9 by 4. By cancellation, it reduces to 9 by 2. Let us proceed. Third term A3 will be 3 into 3 square plus 5 by 4, which on calculation reduces to 3 into 3 square is 9, 9 plus 5 by 4, which is 3 into 9 plus 5 is 14 by 4, which reduces to 3 into 7 by 2, which is 21 by 2. Last term to be found is the fourth term. Since the question demands you to find first 4 terms, is 4 into 4 square plus 5 by 4, and this on calculation reduces to 4 into 4 square is 16 plus 5 by 4, which can be written as 4 into 21 by 4, and which gives a whole number (21). So, these are the first 4 terms. If you list the first 4 terms alone, it will be 3 by 2, 9 by 2, 21 by 2, 21. Hope I have not made any calculation mistake. It is a good exercise to recheck. Next example demands you to find 9th term of the sequence an, n is equal to 1 to infinity, where an is given by minus 1 power n minus 1 into n cube. The 9th term, namely A9, can be obtained by plugging n equal to 9 in the general expression. So, A9 will be minus 1 power 9 minus 1 into 9 cube, which is equal to minus 1 power 8 into 9 cube, which is minus 1 power 8 amounts to 1, and 9 cube is 81 into 9, which is 729. That solves the previous problem. In the next example, you are asked to find first 3 terms of the sequence an, n is equal to 1 to infinity, where an is described by the formula an is equal to an minus 1 minus 1 for n greater than 2, and a1 and a2 are 2. I would suggest you to recall the rabbit problem example, where instead of writing an in terms of n, we write an in terms of its previous terms, describing a sequence such a manner that the nth term is expressed in terms of previous terms is called recurrence relation, or it is called recursive definition of the sequence. And here you are given with the recursive definition. an equal to an minus 1 minus 1, and the recursion starts with the terms a1 and a2, which is given to be 2. In fact, a1 is 2 and a2 is 2, which is given. This is how you can start the recursion. For n greater than 2, an is defined as the previous term minus 1. Therefore, a3 will be put n equal to 2 in the recursive relation. a3 will be a2 minus 1, and a2 is given to be 2, 2 minus 1, which is 1. So, you should observe that unlike in the case where sequence is described with a formula in terms of n, in the recursive definition, to get a particular term, we may have to find the previous term and then plug that previous term and so on. Let us continue with one more example. Find first 4 terms of the sequence an, n is equal to 1 to infinity, where an is described using a1 is equal to 3 and an is equal to 3 into n minus 1 for n greater than or equal to 2. Observe that in this example as well, the sequence is described with a recurrence relation. First term is given to be 3, the second term a2 using the recurrence relation is 3 times a1, which is 3 into 3, 3 square. Third term a3 is equal to 3 into a2, and a2 we have previously found, which is 3 into 3 square, which is 3 cube. a4 is 3 times a3. This is by the recursive definition, which is equal to 3 times a3 we have found in the previous step, and which amounts to 3 power 4. These are the 4 terms asked to found. But then in this example, let us see whether we can find an in terms of n. Remember that the recurrence relation given an is 3 into an minus 1. Using the recurrence relation, an minus 1 is 3 into an minus 2, and an minus 2 is 3 into an minus 3, and so on. Applying this in succession, we will see that it will be a1 times, observe that 1 can be thought of as n minus n minus 1, so that the power of 3 with which a1 to be multiplied is 3 power n minus 1. See the pattern. When we have a n minus 1, power of 3 is 1. When we have a n minus 2, power of 3 is 2, and so on. So, when we have a1, that is a n minus n minus 1, the power of 3 is n minus 1. A1 is given to be 3, so this is 3 power n minus 1 into 3, which is 3 power n. In this example, even though as such the sequence is given in terms of a recursive definition, using that recursive definition successively, we could write an in terms of n. This is called closed form expression. For an. The nth term an is expressed as a function of n, so that given any n, we can directly find what will be the term corresponding to the given n without finding the previous terms. This way in which an is expressed solely in terms of n is called closed form expression. This example illustrates that there are cases where, though the sequence is expressed originally in terms of a recursive definition or a recurrence relation, ultimately we can come up with a closed form expression for the same sequence. This is called solving of recurrence relation. Of course, there is a systematic theory to solve given recurrence relation. We are not going into the details of it, but this example is expected to shed light that there are cases where a recurrence relation given for a sequence can be solved to obtain the nth term of a sequence in terms of n. There are cases where the recurrence relation is preferred rather than formula in terms of n. Having said this, let me continue with few more examples, but this time with a different intention. Consider the sequence an, n is equal to 1 to infinity, where the nth term an is given in terms of n using the expression an is equal to 1 by n. To be explicit, let me write few terms of this sequence. First term is 1, second term is 1 by 2, third term is 1 by 3, fourth term is 1 by 4, so on and so forth. Recall, the same thing can be expressed graphically, in fact in two ways. Let me use the first way of marking the terms in the real axis. This is the real axis with natural numbers, or more specifically non-negative integers indicated. The first term is 1, so this is a1. Second term is 1 by 2, it is midway between 0 and 1. This is a2, 1 by 2, and a3 is 1 by 3, somewhere here. A4 is 1 by 4, it is midway between 0 and A2. So, this is A4 and so on. Do you observe either from the list of elements in the sequence or from the graph that we have plotted that as we progress towards the end of the sequence 1, 1 by 2, 1 by 3, 1 by 4, etc., etc., the terms get closer and closer to 0, because as you progress towards end of the sequence, n increases, number corresponding to the place, first place, second place, third place and so on increases, that is n increases. The number occurring in nth place is 1 by n. So, as n increases, 1 by n keeps on decreasing and it eventually comes near to 0. So, the observation in regard to this example is that as we progress towards the end of the sequence, in other words, as we increase n, the term a n becomes close to a fixed number 0. That is clear from the graph a1, a2, a3, a4 that moves towards 0. Keeping this in mind, let us proceed with another example. Consider the sequence 0, 1 by 2, 2 by 3, 3 by 4, etc. As I told you previously, it is always suggestive, if possible, to write what is the term in nth place. If you see the pattern, it is n minus 1 by n and so on. Consider this sequence. Now, let us do the similar exercise as in previous example, that is, let us observe what happens to this sequence as n becomes larger and larger. One way to do it is draw the graph. I mean, represent the sequence using graph, using the first method I suggested. Here is 0, here is 1, let us say 2 and so on. The first term is 0, this is a1. Second term is 1 by 2, which is midway between 0 and 1, this is a2. Third term is 2 by 3, which is greater than 1 by 2, you can observe it, but it is less than 1. So, somewhere here is a3. a4 is again less than 1 because it is 3 by 4, but it is greater than a3. So, somewhere here and so on. You can observe more and more points a5, a6 and so on. You can see that the terms, as far as this example is concerned, comes closer and closer to 1. It can also be observed in a different manner without relying on the plot. Let us write the term 0, 1 by 2, 2 by 3 and so on. The nth term, namely n minus 1 by n, can be rewritten as 1 minus 1 by n, isn't it? Now, the terms are 0. The second term is actually 1 minus 1 by 2. third term is 1 minus 1 by 3 and so on, nth term is 1 minus 1 by m. Now, can you guess what happens when n becomes larger and larger? As n becomes larger, 1 by n comes close to 0, so that 1 minus 1 by n, those numbers will come near to 1. Thus, as far as this particular example is concerned, as n increases or as you move towards the tail end of the sequence, the terms of the sequence are coming close and close to 1. Recall in the previous example, namely the sequence 1 by n, as n becomes larger and larger, the terms were becoming very close to 0. And in this example, as n becomes larger and larger, the other way of saying it is, as you progress towards the end of the sequence, the terms gets closer and closer to 1. Let us continue with another example, namely the sequence root n, n is equal to 1 to infinity. To be explicit, let us list few more terms: 1, root 2, second term, root 3, third term, and so on. Nth term is root n, and so on. It's an infinite sequence. Let us do the exercise we have done previously, namely, try to observe what happens when n becomes larger and larger. Remember, when n grows larger, root n grows larger. For instance, root of 100, which is 10, is greater than root of 2. Root of 10,000 is greater than root of 100, namely 10, and so on. Thus, when you progress towards the end of the sequence, the terms are becoming larger and larger, and this growth is not controllable, in the sense, as you go on, you can increase the value of the terms. Thus, unlike in the previous example, in this example, we don't observe that as n becomes larger and larger, the terms of the sequence become close to some particular value. If you graph it, it will be like first term is 1, second term is root 2, which is greater than 1, third term is root 3, which is greater than 1 and also greater than root 2, a4, which is root 4, which is 2, and so on. So, whatever large number I give, you can find a term in this sequence such that that term is larger than number given by me. For example, suppose I say 100, you can always find a term in this sequence greater than 100. For instance, if you find a 10,001, it will be actually root of 10,001, and root of 10,001 is greater than 100. So, given 100, I can find a term, namely 10,001th term, which is greater than 100. Now, suppose I give some other number larger than 100, still you can find a term am greater than the given number k. In other words, as you progress, the terms of the sequence are becoming larger and larger. So, you do not find any fixed number to which the terms are becoming near. Now, let us proceed with another example. Consider the sequence 1, minus 1, 1, minus 1, etc. The nth term is minus 1 power n plus 1. First term is minus 1 square, which is 1. Second term is minus 1 power 3, which is minus 1, and so on. Here, as you progress towards the end of the sequence, in other words, when you make n larger and larger, what happens to the sequence is it bounces back between 1 and minus 1. If n is a large number which is an odd integer, then n plus 1 will be even and the term will become 1. And if n is a large number which is an even integer, then n plus 1 will become odd and hence the term will be minus 1. Thus, as n progresses, the terms will be either 1 or minus 1. We cannot say it definitely. It depends upon what is the value of n. So, we cannot find a number to which the terms of the sequence come closer. Consolidating the previous examples that you see, in the first example, namely 1 by n, what happened was as n increases, the terms changes, but then it becomes nearer and nearer to 0. In the second example, as n increases, the term comes nearer and nearer to 1. In the third example, as n increases, the terms becomes larger and larger, so that we cannot say that all terms will be ultimately near to some fixed number. In the last example, though the terms are not becoming larger, either it will be 1 or minus 1, but still we cannot find a number so that all the terms are coming close to this particular number. These examples should illustrate that there are cases where sequence behave in such a manner that as n increases, term become close to a number, and there are instances where as n increases, the terms of the sequence will not remain near a fixed number. To distinguish these two cases, we introduce the terms called convergent sequence and divergent sequence. Informally, A sequence is said to be convergent if as n increases, the nth term of the sequence a n comes near to a fixed number L. Let me write. Informally, a sequence a n is equal to 1 to infinity is said to be convergent if as n increases, ans become sufficiently close to a number L. Keep the first example in mind, namely the sequence 1 by n. As n increases, the terms become close to 0. Remember that the number L may not be a term in the sequence. For example, in the case of 1 by n, terms are becoming closer and closer to 0, but no term is exactly 0. Such sequences for which there exists a number L such that as n increases, all the terms of sequence an comes near to L is called convergent. This L is called limit of that sequence. In notation, we write it as limit n tending to infinity a n is equal to L. L is called the limit of the sequence, and such a sequence is called convergent. If there is no number L for which as n increases a n come close to L, then the sequence is called divergent. Those who recall limit of a function can understand that this is a particular case in the sense that sequence is also a function. Let us not go into the details of this convergent sequence, etc., but at least informally, what's the meaning of a sequence to be convergent and what's the meaning of limit should be clear. We will not dwell on the precise definition of convergence, how sequence convergent and the limit of a function which you studied, etc., are connected. Having known the informal definition of convergence, let us practice with some more examples. Consider the sequence an n is equal to 1 to infinity, where an is equal to 5 by n square. Of course, here I used a bracket instead of a set notation. I should say that a sequence can also be represented by using parentheses like this instead of set notation we have used so far. That is, instead of writing a sequence like this we can write in this manner as well. In fact, I feel this is more suggestive in the sense that it will not be confused with a set. Sequence is ordered, whereas set there is no specific order of elements. Now, let us consider the sequence a n where nth term a n is given by the formula phi by n square. Now, I would like you to guess what happens to the terms of the sequence as n becomes larger and larger. Let us list a few terms. First term is phi, second term is phi by 2 square, third term is phi by 3 square, fourth term is phi by 4 square, and so on. Observe that the numerator is fixed to be phi and denominator gets increased like 2 square, 3 square, 4 square, etc. The 100th term will be phi by 100 square, etc. So, as you progress, as n becomes larger and larger, the terms phi by a very large number goes to 0. So, almost all terms after that will be 0. Not almost all term, in fact, every term will become closer and close to 0 except finite number of terms. Okay. In other words, this can be represented by limit n tending to infinity phi by n square is 0, or the sequence phi by n square is convergent and 0 is its limit. As a final example, consider the sequence a n is equal to 1 to infinity, where a n is given by 4 minus 7 n power 6 by n power 6 plus 3. The question is, observe what happens to the terms of the sequence when n becomes larger and larger, or determine whether the given sequence is convergent or not. As such, by the given form, it may not be straightforward to see what happens to a n as n tending to infinity, but let us do some manipulation. A n can be written as, I am taking an n power 6 common from numerator. So, it will be 4 by n power 6 minus 7 by n power 6 1 plus 3 by n power 6. Now, n power 6 cancels out and nth term can be rewritten as 4 by n power 6 minus 7 by 1 plus 3 by n power 6. Now, as n becomes larger and larger, 4 by n power 6 becomes closer and closer to 0 because denominator n power 6 gets increased. So, this goes to 0. So, the numerator reduces to minus 7 as n becomes larger. Similarly, the denominator 1 plus 3 by n power 6, the second summand, namely 3 by n power 6, goes to 0 as n tending to infinity. 3 by n power 6 become close to 0. So, denominator becomes close to 1 plus 0. So, as a result, a n, when you observe as n becomes larger and larger, comes near to minus 7. Thus, the given sequence is convergent and the limit is minus 7. We will discuss more about sequence and then enter into series in the next class. Thank you.